Hello all, welcome to the hands-on exercise for this week's. In this hands-on exercise, we are going to do some logistic regression analysis using Julia from genetics dataset that are available in R. So first, I am going to start R. In R, you have this genetics in the package. There is a called GAP package, genetic analysis package, and in the genetic analysis package there is a data called FA data, Friedreich ataxia data. We are going to use this data. Was first appeared in the genome research in 2001. We are going to use this data to implement logistic regression using Julia. So one of the advantage of Julia is many of the packages that are available in R are also available in Julia, or from Julia you can call those dataset using R dataset package. So let me go to Julia, my Jupyter notebook. I have prepared this Jupyter notebook to some extent, and I will use this Jupyter notebook to extend this thing. So here is in our data set, you can see I have first what I'm going to do. Let me just open this. So maybe I'll just do, okay. So like here it is Friedreich ataxia data. So I'm going to give a name of, so maybe logistic regression analysis of data. Okay. So here is the source of the data I have given, and so maybe I'll just run it like this. And this is the first thing I'm going to call CR Rao, R dataset, stable RNG, and stat models. Okay. So this is first I'm going to call this packages. Then I'm going to, from the R datasets, I'm just calling R dataset. This is the name of the package, GAP package from R, and FA is the name of the dataset. So let me just call this. So here we have the first column is the target column Y. It has 0 ones, and then there are 12 columns. Okay, there are 12 columns which we will be using as a predictor variable. Now what I'm going to do in this, if you just instead of actually run the first thing, so here I'm going to run this piece of code. In this piece of code, I'm going to split the data frame into train and test. You can see that first I'm taking the percentage between 0 and 1, and then I'm collecting the IDs of the data frame and then kind of shuffling them, and 70% of that I am keeping it in the train, and rest of them I'm keeping in the test, and then I'm returning train and test. So I'm calling this split data frame function and splitting it into train and test. And so this is the first 10 rows of the training data set. Then first I'm going to implement the maximum likelihood of method of logistic regression. In that I am going to call fit from the CR Rao. First I have to provide the formula. Y is the target, and then all the predictors that I want to fit, all the predictors that I have given here, and then the data frame is train. I want to fit a logistic regression with logit link. So if I just run this, so here is the output. Now if you see, the p-value for most of these loci are not great, except the third loci, third predictor, loci 3, and then these are also not effective, and loci 11 and 12 have effective. So these are the out of 12 loci, only 3 are effective kind of effect on the target variable. Now using this model, we can have a predictive, we can predict the probability score on the, on the trained data set, on the entire data set. Or similarly, if you just say predict, you could call the predict function from CRRAW and provide the model name and the test data set. You can, so we can, I don't need this, actually I need this one. I need to calculate the predict on the test data set. So this gives me 39. The probability of a particular data point is 1 or 0. That will be based on this test data set. And then eval matrix is a package you can call, and that will help us to do the evaluation. And test.y is going to give me the either 0 or 1. So in the test, from the test data set, I'm just taking the y. And binary eval report, if I just give the find test.y, the actual y values and the predicted score. Okay, so predict MLE contains the all the probability scores, right? So now if I just run this gives me the confusion matrix. Similarly, now if I want to implement the Bayesian logistic regression, say logistic regression, so with say reach prior model. So here if you see that y follow Bernoulli mu I, where mu I follow alpha plus xi transpose beta, and like here is that is my likelihood model. And then well, actually I should not say this, actually mu I, there should be like pi it should be pi actually, and then pi is equal to this logit mu I think now that is a right way of writing it. And then mu I equal to xi transpose beta, alpha plus xi transpose beta, and then so alpha follows say normal 0 and beta follow normal 0 v sigma, sigma follow inverse gamma, and v follow some another inverse gamma. Then this model, this is typically we will implement as ridge regression model. Now what we can do, if you see the way we have implemented the regression, simple logistic regression model, almost similar way we can implement it here, except that at the end I am just using prior reach. Okay, I'm just calling reach prior here, and if I just run it, so it will take few seconds maybe. Okay, it is taking about it took about all right, so it took most of the, and if you see r hat, all of them are kind of near 1, so that means if r hat is near 1, that means the convergence has taken place. And if you see 13 entirely negative, but 12 is not negative, it includes the confidence interval. If I see the 2.5 percentile point and 90. So let me just explain you this Bayesian statistics a little bit. So this is first the coefficient estimates, and these are the standard deviation. So if I have to compare it with the likelihood estimates, right? So these are my coefficient estimates and these are the standard error. So that's how you will see it here. These are my coefficient estimates. So beta 1, you will see including beta 1, there are 13 betas, whereas here I have actually 12 betas and alpha, so total 13 betas I have. So the first one is the intercept, beta 1, this is intercept, and then or here it is intercept, and then you have 12 coefficient corresponds to each of the predictor. Now these are the some Monte Carlo standard error, and if smaller Monte Carlo standard error indicates that the most likely it has converged nicely. And another statistics is called R hat. If R hat is close to 1, that means the MCMC convergence has taken place. So Bayesian statistics in this case are being implemented using Markov chain Monte Carlo algorithm and not gradient descent algorithm. So it is a Monte Carlo simulation based technique that they have increased. And here for inference, what they do, they give a 95% confidence interval, and if you look into the 95% confidence, that the last coefficient does have an effect sort of, and the third coefficient also does have an effect. It's a positive and this is a negative coefficient, and rest all of the coefficient includes 0 some way or other. So there none of them have actually any effect on that. So if I just do a plot, simple stat plot, so here is the plots. You see they have decently converged, nicely converged. Okay, all of them pretty much decently converged. Here I am doing the predictive error, and here I have to do the confusion matrix. I have to compute. For some reason binary evaluation of the report is not working. I will come back to you on the same. So I will say take predictive ridge as that, and then if I just use that, so these are the confusion matrix that we have found. So I'm not sure if it is correctly done, so I'll check with this. Now if you look back, if you go to the say, if I am now interested in implementing say Laplace prior, how do I implement? So if I am interested in implementing say Bayesian logistic regression, Bayesian logistic regression using Laplace prior. Okay, so if I have to do that, all I have to do is just copy this guy from here, and instead of, I will just name it as Laplace, and instead of prior ridge, I will just say prior underscore Laplace. So prior underscore Laplace. Okay, the rest of the thing will be exactly same. And now if you just run sorry, I think Laplace, there was a spelling mistake. Yeah, now I think it is done. Yeah, so okay, looks like Laplace also has been implemented very fast, and it's kind of 1500 simulation samples are being created from 1500 samples, first 500 is being considered as a burn-in, and from 501 to 1500, 1000 samples, based on 1000 samples it is being created. And similar kind of inference you can see you can do based on the credible interval. Now if you interested in, say, doing Cauchy interval, Cauchy prior, so all you have to do is just take this information, and now if I want to introduce, say, all I have to do, just take this, and instead of Laplace prior I want Cauchy prior. Okay, Cauchy, Cauchy prior, but not Laplace. So I will just, instead of Laplace, I will say Cauchy prior. So I'll just effectively, if I just write the C and then tab, will fill up the rest of the thing. If I just write the C and then tab, if you just press tab, it will fill up the rest. So instead of Laplace, I want to name it as a, say, Cauchy prior. So for some reason the evaluation methods are not working properly. I will correct those and I will share the correct notebook with you guys. For some reason it is not working, but as you see here also, pretty much all R hats are, first thing you should check in the Bayesian statistics, whether all R hats are very close to 1 or not. If it is indeed 1, close to 1, then you are in good shape. And here also you can see the third predictor is all positive and the last predictor is all negative. Rest of the all predictors are essentially either or including 0. Their 95% confidence interval is including 0. So similar consistent inference that we are getting from all of the priors. Now let us see what else do we have other than Cauchy prior. We have also t-distributed prior and then horseshoe prior. Horseshoe prior is very popular. Let us try to implement the horseshoe prior. Okay, so let us try to implement the horseshoe prior. So let me just do that. And here is the, so all I have to do, just go copy this model, and now instead of, in the prior area, just instead of Cauchy prior, just say horseshoe. So I will just say H and then tab, it will fill up the rest, and I'm pretty much done. Of course I want to change the name to horseshoe prior and run. Horseshoe prior may require a little bit of more run, maybe 1000 simulation is not enough because it has a lot of parameters in it. So we will see. Interesting, but we are seeing that most of the parameters have been converged. So okay, but unfortunately it is not printing all the parameters. Okay, that's in Jupyter notebook, that's sometimes a problem. So what I will do, I will run it in the maybe Core Jupyter notebook, Core Julia. So I will open Core Julia so that we can see the results. Okay, so I'll just call the let me just run this few lines there. Okay, and then if I will just call this guy. Okay, and I will call the split function, train and test. and then okay. Then finally I will just run the last data set, last model. Okay, let us see how much time it takes. Yeah, it's relatively fast actually. Okay, so all right, so if I just write this, yeah, now I can see that all the parameters here are being printed nicely. You know, our hat is, all the R hat are very close to 1, means convergence did have taken place. That is a very good news for us. And then for each parameters, if we will see how this for each coefficient there will be a scale parameter in the horseshoe prior. So each scale parameter confidence interval are also being printed. And now what you can see that the third one as expected is also very strongly positive, and the last one has a very strongly negative, whereas these ones are not, you know, very strongly positive or negative. So if I go back and if I just do the plot, let me do a plotting, and you will see typically horseshoe prior behaves a very interesting way. So let me just try to do the plotting. So using okay, let me just see if I can create this plot here. Horseshoe prior chain. Yeah, it is better. So first are all lambda parameters, and then we will see here the betas. Now you can see that betas are all very close to 0. They're bit close to zeros, and they're very close to sharp to the 0 and not too much. So they see there are a lot of, they're not sticking. And then the third one, this is the second one, and then this is the third one. They're all positive, and the entire thing is positive being shifted. Okay, where the others are like, very stick to the, very stick to the 0, and then they have a flat distribution. So this is a very peculiar of the horseshoe prior. They have lot of mass on the 0. It tries to put, and similarly, but when it has because it has a lot of mass on the tail in the prior itself, when the posterior, if it have any coefficient has true positive mass on the non-zero place, then it gets, it's nicely picked up that behavior also. So you can implement horseshoe prior in genetic, in logistic regression very easily with just one line of code using CRO package. The detail about the horseshoe prior are given here. I have given that. All these things, this is if D is a distribution. Distribution could be normal, Bernoulli, anything. Mu I is X transpose beta. So you have to be mu I is in with the distribution with respect to a mean and variance or standard deviation. And then beta follow normal, alpha follow normal, but conditional normal, The scale parameters are follow Half-Cauchy distribution. These lambda j's follow Half-Cauchy, sigma follow Half-Cauchy, and the tau distribution also follow Half-Cauchy. So with this is a very peculiar kind of, very popular actually in the Bayesian literature, and you can implement horseshoe prior using CR Rao very easily. So I hope you enjoyed this video, and we will keep doing more such analysis using CR Rao in the coming videos. Thank you very much. See you in the next video.